Let's take a look at graphing and all the different types of transformation on a logarithmic function together. This is the function that we're going to work with. We have f of x is equal to 3 plus 2 times the natural log of the quantity of negative 1/2 x minus 1. To better understand what's going on with this function, it's important to understand the parent function, which is going to be f of x is equal to ln of x, or the natural log of x. So while this is the parent function for the natural logarithm function, let's go ahead and figure out what effect this 3, 2, negative 1/2, and negative 1 have on this function. Let's focus in on the transformations for a bit. So this is our general formula for our logarithmic functions with their transformations. And this is the function that we're dealing with for this particular practice problem. While these are laid out generally the same way, there are some pieces we can move around a little bit and manipulate so that they look a little bit more in line together. Rearranging this a bit, we're going to get this right here. So basically I just moved the 3 in front to in the back, and then I just went ahead and factored out this negative 1/2 from both of these terms so we could see what our k value is going to be. So you can always go ahead and distribute this out also to get back what we started with, but this is going to help us figure out a couple more details along the way. Alright, first letter up we have this a value. That a in this case is going to be 2. So if we know a is equal to 2, that's going to help us know what's going on with our vertical stretches or shrinks, also as well as our vertical reflections, but in this case we're not going to have one. Another variable that will affect the vertical part of this transformation is going to be the c value here. Notice that we have this plus 3 that we moved to the end here. So because c is equal to this positive 3, we know that this function is going to shift up 3 units. Now, what about this k? Well, k in this case is going to be equal to negative 1/2, and that serves two purposes, right? The fact that it's equal to a negative value means that we're going to have a horizontal reflection across the y-axis, and then the fact that we have this value of 1/2 lets us know if we're going to have a horizontal stretch or compression, also known as a stretch or a shrink. And finally, we have this value for d. In this case, we have this d value, which is going to be a 2. Now, in order for this to be a plus 2 that we have in front here, keep in mind that d actually has to equal negative 2, because if you take away a negative 2, that's how we have a plus 2 there. Alright, so now that we know the details a little bit better, let's think about what's going on with all of these transformations. Alright, so starting off with a horizontal stretch or shrink, in this case we're going to be having a horizontal stretch, so we're going to go ahead and say yes to that one. Now, when we're finding out the factor that we are doing this horizontal stretch or shrink by, it's always going to be 1 over whatever k is. Now, in this case, k is going to be this negative 1/2, so it's going to be 1 divided by this negative 1/2, right? Now, if you go ahead and do 1 divided by negative 1/2, that becomes 1 times negative 2, so that's going to equal this negative 2 value. What about a horizontal reflection? Well, that depends on the value for k, if k is positive or negative. Because k is negative here, then we're going to go ahead and say that we do have a horizontal reflection. So we'll go ahead and say yes, and that's because k is equal to this negative 1/2. As for the horizontal translation, we're going to go ahead and say yes to that because we have a value for d that's not 0. Now, if d happened to be 0, then we wouldn't see it, but if d is any other number, then we're going to have some horizontal translation. So because we have this d equals negative 2, we know that this function is going to be moved 2 units to the left compared to the parent function. Looking at the vertical stretch or shrink, in this particular case, we're going to have a stretch. We're going to go ahead and say yes to this over here, and that's because the value of a. So since a is equal to this value of 2, that means we're going to be stretching because it's greater than 1. If it happened to be between 0 and 1, then we would have a shrink instead. For the vertical reflection, we're going to go ahead and say no for this one, just because a is equal to a positive number, right? If a was equal to a negative number, then we would say yes. Finally, for the vertical translation, that's going to be up and down movement, we're going to go ahead and say yes for this particular problem, and that is dependent on the value of c. So if c was 0, then we would have no vertical translation, but since c is equal to positive 3 here, then this whole function is going to be moving up 3 units compared to the parent function. Alright, so now that we know all the different type of transformations that are happening to this function, let's go ahead and see if we can find out more information about this function that we can see on a graph. Alright, starting off with the asymptote. For exponential functions, we have a horizontal asymptote. For logarithmic functions, we have a vertical asymptote. Now, the default one for the parent function is going to be at x equals 0, right along the y-axis. But in this particular case, this vertical asymptote is going to be moving. Now actually, if we look up here, we saw that there was a horizontal translation that was going to be to the left 2 units. So that actually moves our vertical asymptote to the left 2 units. So our new vertical asymptote is going to be at x equals -2. All right, next to find out our y-intercept, then we're just going to plug in x equals 0 in for x and find what f of x is equal to, and that will tell us our y-intercept. So again, this was our original function, and if we go ahead and find f of 0 here, then we're going to have 3 plus 2 multiplied by ln of -1/2 times 0 minus 1. And if we do that, we're going to leave this 3 plus 2 times ln alone for a moment here, and looking inside the parentheses, -1/2 times 0 minus 1 is going to equal -1. Now this presents a little bit of an issue because we can't go ahead and take the natural log of -1 here, so this is going to be undefined. So since that's going to be undefined, that also lets us know that this logarithmic function is not going to have a y-intercept. It just won't cross it. As for the domain, typically it is going to start where the vertical asymptote is and go to the right in forever in that direction. However, because we have a horizontal reflection across the y-axis and everything is being moved 2 units to the left, we now know that the domain is going to go to the left forever, or towards the -infinity, all the way up until this -2. That's going to be the right bound of this function. So the graph will not hit that -2 for the x value. As for the range, well, the range for all of these logarithmic functions is going to be from -infinity to +infinity, meaning it will go down forever and it will go up forever. Now what about end behavior? So as x approaches -infinity, or as the x values approach the left on this graph, we're going to know that f of x is going to be approaching +infinity, so it's going to be going up forever. And on the other side, as x approaches +infinity, or as the graph goes to the right, f of x is going to be approaching -infinity. Now, just so you know, these 4 things are a little bit harder to kind of visualize until we see the graph, so hopefully these will make more sense once we graph it, because some people like doing that first and then filling in these later. So now that you have them, let's go ahead and just check them later once we see the graph. Now let's go ahead and start graphing, but what I'm going to do just to start is put that vertical asymptote down at x equals -2. So let's just put that down. Alright, so there is our vertical asymptote, and this function is going to exist to the left of it, just because typically it's to the right of it for the parent function, but because everything is being flipped or reflected horizontally across a vertical axis, everything's going to be to the left of this asymptote. Let's go ahead and grab our function that we had earlier, and let's start by making a table together so we can understand what's going on a little bit better. Alright, so here's our function and each of those values of a, c, k, and d, and they're going to let us know all of our transformations. And so we're going to go ahead and take a look at the parent function table first, and then apply some of our transformations onto it to get our new table to make our graph. So we have a bunch of rows for this table. I'm just going to go ahead and choose 3 x values I'm going to want to use for this table that I think are going to be pretty nice and easy. So I'm going to go ahead and choose 0, 1, and e. And let's just ignore the rest of these boxes. However, if you wanted to make up more rows just to get some extra practice, feel free to do so. You're just going to get some tough decimals to work with. First up, we have x equals 0. So if we found f of 0 or ln of 0, that's going to be undefined. And hopefully that makes sense because we're going to have a vertical asymptote at x equals 0 on the parent function. Then if we say x is 1, f of 1 or ln of 1, that's just going to equal 0, right? Because e to the 0th power is equal to 1. And then one more here, we have e, which is again about 2.71828. If we take ln of e, hopefully that makes sense that that's going to equal 1. That's something that you've seen before with our properties of logarithms. All right, so while that's the parent function, let's look at the given function that we actually have. So how are we going to go from this parent function over here to this more complicated function that we have in this problem? Using a quick mapping formula, all the original points that are x, y in the parent function table will turn into these new coordinates on our actual function. So for each x on our parent function, we're going to go ahead and divide by k, then add d. And then for each of our y coordinates, we're going to go ahead and multiply them by a, then add on c. Starting with our x values, we're going to take each of them and then divide by k first. Now k is equal to -1/2 for this function, so we're going to take each of them and divide by that. And then we're going to add on the d value. So d is going to be -2, so we're going to add on -2 to each of these values. So for x equals 0, if we go ahead and multiply it by -1/2, that's still going to be 0. Then 0 plus -2, or 0 minus 2, is going to be at -2. So our new x value here is going to be at -2. Then when x is equal to 1, if we divide that by -1/2, that's the same thing as multiplying it by -2. That's going to equal -2. And then -2 plus -2 is going to equal -4. So that's going to be our next x value. Next we have this e here. If we go ahead and divide that by -1/2, that's going to be e times -2, or -2e, and -2e plus -2 is just going to be this -2e minus 2. So I'm just going to write that as -2e minus 2 for now. Moving on to our y values, we're going to multiply them each by a, then add on c. So let's go ahead and write that down here. We're going to multiply by a. In this case, a is going to be 2, so we're going to multiply them each by 2. And then we're going to add on c, so we're going to add on 3 in this case. First up, we have this undefined because we have a vertical asymptote here, and that's not going to change. So let's just go ahead and say that our vertical asymptote just moved over 2 units to the left, which is what happened, and that's going to just stay as undefined here. Next, if we take the 0 and we go ahead and multiply by 2, that's still going to be 0, then plus 3, that's going to equal 3. And then finally here we have y is equal to 1, so if we go ahead and multiply that by 2, that's going to be 2 plus 3, and that's going to equal 5. So let's go ahead and plot that right over here. And again, let's just go ahead and use these 3 points that we have here. That should be more than enough. Now, while keeping this exact is pretty nice, if we want an approximation for the actual graph part, let's say this is going to be -7.44. That's if you plug into a calculator, that's going to be the approximation for this -2e minus 2. All right, now moving over to the graph, we've already graphed this vertical asymptote. That's going to be located right over here where x is equal to -2. Notice how the y value is undefined because that's going to be anywhere along there. The graph won't exist on that asymptote. Moving on, we have this -4, 3. So -4 would be to the left 4 of the origin, then up 3. That's going to be right here. Okay. And then for this point of -2e minus 2, or -7.44, 5. 1, 2, 3, 4, 5, 6, 7. It's going to go off the page here, so I can't even put it. I think it's going to be to the little bit left. We have 7 boxes. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. So I think it's actually going to be maybe somewhere around here. So I'm going to just approximate this, but it's definitely not perfect, but I just wanted to put that one on here. If we go ahead and make a rough sketch here and go ahead and connect these dots, we're going to get something that looks like this. Now let's go ahead and take a look at this in conjunction with our end behavior and domain and range, just to make sure everything makes sense there. So if we take a look, we can see that the domain is from -infinity to -2. So again, it is going to the left forever towards -infinity, and it'll never reach that x value of -2, even though as we're getting closer and closer to it. For the range, it is going to go down forever here, you can see that, and it's going to go up forever. As it moves to the left here, it's still going to keep moving up. For the end behavior, as x goes to the left, you can see that the y values are going to go up. So that's what's happening over here as you move to the left. And then what about the other end behavior as x is moving to the right, or as x keeps approaching the right for forever here, it's going to be f of x is going to be approaching -infinity. But keep in mind the end behavior here really isn't going to be reaching positive infinity. I guess more technically it would be x is approaching -2 because of that vertical asymptote. So I got a little carried away earlier with saying x would approach that positive infinity for the end behavior. Keep in mind that it actually does approach this -2, and it doesn't actually approach positive infinity because of that vertical asymptote. So try to keep in mind for that and don't make the same mistake I did. So that wraps up this pretty extensive video on an example where we're dealing with graphing a logarithmic function with lots of different transformations and some details about this function in general. We also went ahead and graphed it, so hopefully you can see that visual and making a table and looking at the parent function and given function and seeing how we could create a table to make it a little bit easier to graph. So if you found the video helpful, please consider giving it a thumbs up and sharing with a classmate or a friend who might also find it helpful. And as always, keep up the great work that you're already doing, and I'll see you in the next one.